In this mini lecture, we explore the idea of compound actions. We expand on this idea that they are not thread safe if you cannot guarantee atomicity of compound actions. We look at two different examples of compound actions, and we start to explore some ways that you can make thread safe compound actions by making them atomic with respect to each other. So one compound action we saw in the previous mini lecture was just this plus plus count. This is now in the context of a servlet. So a servlet is a program that sits on the server waiting for a browser to make a request. And the important thing for our point of view is that the servlet, when the service request comes in from the client, that these can be multiple threads. So you can have multiple threads running through this service method in the servlet at the same time. And so as we saw before in the previous mini lecture, this plus plus count is not thread safe, right? If you have multiple threads coming in here, there's no guarantee that the counts will be unique. And because this is 3 operations, you can have one thread working on this plus plus count while another thread is working on get count, and the results of this are undefined. So anytime you have a multiple operation where you have multiple threads working on that operation and the threads can be interleaved, the results are undefined. And that's what we talked about in the last mini lecture, and is this figure 1.1 in the Java Concurrency and Practice textbook. What takes a little bit of experience to see is that this multiple action is not thread safe, and that really has a lot in common philosophically with code that looks very different. So in this example, also from the Java Concurrency in textbook, you have some expensive object. And what you're trying to do here is what's called lazy initialization. So in lazy initialization or just-in-time initialization, you want to, every time you construct one of these expensive objects, it takes a really long time. So what you're trying to do here is have a cache. So you have a private method, or a private instance of this expensive object, which starts out as null. If you call get instance, you check to see whether it's null. If it is null, you say new expensive object, and you return that instance. So in a single-threaded program, this works absolutely fine. Right? So a single-threaded program comes in, checks to see whether the instance is null. If the instance is not all null, you say new expensive object, and you return the instance. But in a multi-threaded program, this is not thread safe. Okay, and so we can see that, right? If we think about if we make a thread diagram, it's not hard to make a thread diagram to show that this is not thread safe, right? So we have our instance class here, right? Or instance method. Excuse me. I'll say it. Having said it wrong twice, I'll say it correctly the third time. We have this instance of the expensive object, just an instance variable of the expensive object within the lazy init race, right? So this starts out as being null, right? And it's not hard to see that if you're trying to only call new expensive object once, that this is not thread safe. So imagine that we have thread A that comes over here, checks to see whether instance is null, right? And says, okay, instance is null. It is null. So I will go ahead and make the new expensive object, right? So it starts out as null, and then I'm gonna set the instance to be the new expensive object in this line of code here, right? So this first check happens here. The second, the creation of the expensive object and the assigning to the instance variable happens here, right? And we should be starting to develop some tuitions now, right? That the bad luck is going to be interleaving. So if at the same time thread B comes, checks to see whether instance is null, executes this, and then executes this line to set instance there, right? We can see that that although the point of this code was that new expensive object only happened once, it's lazy just-in-time initialization. This is supposed to be a singleton operation where new expensive object is only called once. We can easily imagine an interleaving situation where it's called twice, right? So thread A does this check here, checks to see that it's null. Then with bad luck, thread B comes in, checks to see that it's null, calls the new expensive object, and assigns it to instance. But here, right, thread B has acted in between thread A invoking this line and this line, so new expensive object gets called twice. Now this might or might not matter, right? It might be catastrophic if this thing really is dependent, if expensive object is dependent on being singleton, this could be catastrophic. It might not matter for your code, but the point is it's a race condition, right? So sometimes this is going to be called once, sometimes it's going to be called twice, and it's going to depend on the timing. So this is basic problem that compound actions are not thread safe. And what the book is trying to lead you through here is that this plus plus count that happens here is a compound action, right? It's a read. Multiple threads can read this variable, modify it, and then write it back. And that this is also a compound action, even though it looks really different, because you have one thread. You have this check of the instance variable being null, which needs to be atomic with respect to assigning the instance variable to the new expensive object. Okay, so these are both compound actions. Now, so one way we can force threads to have atomic actions with respect to each other when interacting with our data types is to use Java's built-in thread-safe data structures. And a great example of that is this atomic long variable. So when you make a variable, when you have a variable that's atomic long, here we're setting this to be 0. And now we have two in this example. We have two invocations of this atomic long variable. There's increment and get, and there's get. The atomic long variable makes guarantees. It guarantees that these operations are atomic with respect to each other and with respect to themselves. That is to say, if you have 50 threads that are calling increment and get, they won't interfere with each other, which is to say that the increment and get, each thread that calls increment and get is guaranteed to get a unique value. So we'll see in future lectures how this works, right? But this is a built-in data structure that is inherently thread safe. So imagine that we have a private variable x equals 0, right? And I want to have multiple methods that can operate on this data, right? So I might have a public method called increment, void increment, which would just simply say x plus plus, and I might have another method. Called get, public void get, which would return x. Okay. So what we've just seen is that we know public void, that would be public integer get. Right. So what we know is that these methods are not thread safe, right? So multiple threads can't call increment at the same time. If one thread is calling increment when another thread is calling get, these methods the results are going to be undefined. So we've seen that one way that we can make this thread safe is to not use this variable x as an integer, but instead use an atomic long. Right. So if I use an atomic long and I can still call it x. So this atomic long, which we can start out at 0. So now when I increment this, I can say x dot increment and get. It doesn't really matter, right? It doesn't matter. I'm not going to use the return value here because the increment is just incrementing, doesn't have a return value. And then here I can just say return x dot get. And the only thing is that the integers have to become longs here because this is an atomic long, not an atomic integer. So this is thread safe. This is a thread safe alternative to just saying integer x equals 0. Even if you have 100 threads coming in here, the values that your counter is going to return are guaranteed to be unique, and a thread calling get won't interfere with another thread calling increment at the same time. So that is one option using the built-in data structures to make a thread safe counter. Another way is to use what the book is going to call a monitor pattern. So if you use a monitor pattern, you can go back to making this, let's just go ahead and make it a long so I don't have to change the data types. You can go ahead and just have this be a normal generic data type, and you can go back to the x plus plus here, and you can go back to return x here, right? But what we're going to note in using the monitor pattern is we're going to say that this is guarded by this. And the monitor pattern basically says every time my program touches x, that has to be within a synchronized block. Right, so I'm going to make this block synchronized, which would help if I could spell the word synchronized, and likewise make this synchronized, right? And if I wanted to have some other method, like maybe I wanted to have a method called add 10 or something like that, public synchronized void add 10. And so this would just be x equals x plus 10, right? So anytime I touch this x, because it's guarded by this, I have to have a synchronized block. And what that synchronized block means is that every time that a thread wants to do something to one of these methods, they have to grab the lock, right? And what is the lock? If you just say synchronized, the lock is on this count example, right? So if I say main and say count example CE equals new count example. All of these methods, when I invoke CE dot increment or increment 10 or whatever, right? When a thread comes in here, it says, okay, I need to grab a lock on this CE object, right? On this count example object. So it's the same. The lock is what you would get by typing this here, right? And so which is the same reference as the CE that's here, right? So anytime a thread wants to do something, it has to grab this lock, which means that all of these methods are mutually exclusive with respect to each other. Now, in general, if you have this choice of using a built-in data structure versus using the synchronized, it's better to use the built-in data structure. So that's both because of performance, because these synchronizations we'll see, are going to turn out to be slower most of the time than the built-in data structures, and for simplicity, because let's say that I add a method called subtract 5 or something like that, and I forget to do the synchronization block, subtract 5, right? So now I do x equals x minus 5. I have now destroyed the thread safety of my entire program, because now threads can come in here not having the lock, and the data can essentially be corrupted. Right, so it's complex in a large program. It's up to you, the user, to always grab the synchronization lock, and you might forget to do that. If I use the built-in data structure, so if I go ahead and make this an atomic long x equals new atomic long, like this, right? Now I don't need these synchronized. I don't need these synchronized. I don't have to remember. I don't have to use the synchronized block. It's going to be thread safe without me having to do anything like this, right? I can make just this increment and get as before. I can make this return x.get. Actually, off the top of my head, it's going to be interesting to see if I can figure out a quick way. So if I do x dot add, so here actually I might want to do something like for integer. Well, actually, this add 10 is sort of interesting. Let's not worry about that. We'll talk about that because that actually is going to turn out to require a compound action, and we will we'll talk about that. We'll talk about that later. But for now, right, you can see that that to a first approximation, this code is simpler. And I'll talk about in mini lecture coming up about why I deleted that add 10 and add 5. Okay, so coming back to the book, you have compound actions, which are inherently not thread safe, right? And there's two ways that you can make compound actions thread safe. One is to use Java's built-in data types that are thread safe aware, that are thread aware, and that give you some degree of atomicity. And the other is to use the synchronized keyword. And if you have the choice, you probably want to lean towards using the built-in data types. But in the next mini lecture, we'll talk about some potential problems with the built-in data types that if you're not careful with the way that you use the built-in data types, you can still land yourself into problems. And that's what we'll talk about coming up.